Hello, welcome back to Mrs. O'Graham's Maths. We are doing a practice external assessment from the D&D resources in this video. So first of all, a thank you to D&D for allowing me to use their resources in this way. I have put a link in the video description to their website, so you can order their booklets directly from them, and I highly recommend getting the paper copies and practicing doing these papers by hand and not just relying on digital resources. So we're on the differentiation booklet, which is for standard 91578, and this is the last paper in that booklet, Practice External Assessment number 6. Now, question 1a, we've got cos of 2x plus pi. We're going to differentiate this, so we need to do dy by dx. Now, cos becomes negative sign, so this would be negative sign of 2x plus pi, and then multiply by the 2 because we times by the derivative of what's inside. If you're able to do that all in one step, it'll be minus 2 sine of 2x plus pi. Now, I just realized I picked the wrong color. I do not like that one at all, so just do a quick switch. There we go. Okay, the gradient of the normal for part B. Let's start by writing this in line. So it's minus 6 x minus 1 to the minus 1. So we can see the chain rule on it a little clearer. So we bring the minus 1 down, we times it by the minus 6, we get 6. The power gets reduced by 1. We multiply by the derivative of what's inside the bracket, which is timesing by 1. So we don't need to actually include that this time around. Now, we are working this out where x is equal to minus 2. So when x equals minus 2, dy by dx will be 6 over 2 minus, it's a minus. So minus 2 minus 1 squared, because that's what minus, to the power of minus 2 means it's over that thing squared. So minus 2 minus 1 is 3. This will be 6 over 9, which is equal to 2 over 3. Now that gives the gradient of the tangent, and just note here we want the gradient of the normal. So the gradient of the normal is reciprocal of the negative reciprocal of that. So that's going to be minus 3 over 2. Okay, on to part C, where we want the tangent of this function to be parallel to the x-axis, which means that the derivative will be equal to 0. Okay, so we're finding f dash of x. We've got 2 parts to this. We have one part here being multiplied by another part here. So we need to use the product rule. So we're going to do e to the 3x times by the derivative of what's in that blue part there, so that's a 4, plus 3e to the 3x, so we've differentiated the yellow one, and times by the original blue one. So if we tidy that up, we get 4e to the 3x plus 12x e to the 3x minus 9e to the 3x. Now the 4 minus the 9 we can write as being a negative 5, because they're the same term. And we're going to set that equal to 0 because it's parallel to the x-axis. If we take out a factor of e to the 3x, we get minus 5 plus 12x is equal to 0. Now e to the 3x can't be 0, because if you try to solve that, you'll get a math error. So therefore, minus 5 plus 12x is equal to 0. 12x equals 5, x equals 5 over 12. Okay, for part D, we've got a somewhat tricky function to work with here. We're going to be doing the chain rule on this. Our inside function is the tan squared x, the outside function is the natural log of x, and that outside function wraps around all of that. So you can see that it's a chain rule. So for chain rule, we differentiate the outside, which will be 1 over the thing that was inside of it, and then times by the derivative of the inside. Now The inside itself is actually tan x squared. So that thing itself is also a chain rule. So if we're to differentiate that one, we would have 2 tan x and then times by the derivative of the inside, which is sec squared x. So if we now go through and cancel what we can, we can take a tan out from the top and the bottom. So we've got 2 sec squared x over tan x. Now sec squared is 1 over cos, so 2 over sec squared, sorry, sec is 1 over cos. So 2 times sec squared is 2 over cos squared x. Tan x is sine over cos. So if we've got a division by tan, it's the same as multiplying by cos over sine. So dividing by sine over cos to make tan is the same as timesing by cos over sine. So now you can see we've got some cancelling out of the cos terms, and we'll end up with cos x sine x. So when x is pi by 4, dy by dx will be just popping that into the calculator now, sine of pi divided by 4, that comes to 4. Now you don't necessarily have to do all of this simplifying here if you didn't follow exactly what was happening. You can go straight to doing this so long as you recognise that sec squared is 1 over cos squared. You could put the x equals pi by 4 into it there, but there's no sec button on your calculator, so you would need to turn sec into 1 over cos as a minimum. Okay, part E. So we have this hourglass being modelled by a cone. So it's not exactly a cone, it's more curvy than a cone, but we're going to use a cone to model it to get close to what it would be. So we have this triangle shape. Let's see if I can just make that show up a little better. There we go. So the triangle shape there, where the radius is 9, so from the middle out to the edge is 9, and the height of that triangle cross-section of the cone is 30. Now we haven't been given a rate exactly, but we have been told this information here. So when it's full, it takes an hour to empty, and from that we can work out a rate. If we can find the volume, and we know that it takes an hour to come through, then we would know that that's the rate that the sand is falling through at. So the volume of a cone is 1/3 pi r squared h, and that's on your formula sheet. So this is 1/3 times 30 times 9 squared. Oh, sorry, hang on, I'll do that in order. Times pi times 9 squared times 30. Now that will come to, let's just take a look, 81 times 30 and divide by 3. It's going to be 810 pi. You can write that as a decimal, but it's easier if you just leave it with the pi in it at the moment. So that's in centimeters cubed. So if it takes an hour for all of that sand to run through, then the volume at which, the rate at which the volume is changing over time is 810 pi centimeters cubed per hour. Now, if we're being particular about it, it would actually be a negative, because it's reducing at that rate. Now back to the question to find out what rate it is we're trying to work out, and that is this one here. How fast is the level falling when 20 minutes have elapsed? Okay, so that is thinking about the height of that sand here. So this height here, how quickly is it going down? So we want to work out dH by dt. So if we have dv by dt, how can we use that to get dh? We would need to introduce a dh and divide through by dv. So now we've got to work out something that links h and v together so that we can differentiate it and pop it into this bit of chain rule here. So we have got the formula for the volume up here, but the problem is it's got both r's and h's in. So if we can do something that represents r in terms of h, then we can have v all in terms of h. So back up to looking at this picture that we had up here, where we've got h being the height of the sand, and we're starting with 9 versus 30. And as the height of the sand drops, it will still maintain this similar triangle ratio between it. That 9 to 30 ratio will continue as that sand drops. Those two parts of the triangle will reduce proportionally. So we can say that if we were to do, so I'm just working out where I can fit this in. Okay, so if we were to have, let's do it over here. R over h as our proportions, the radius divided by the height is always 9 divided by 30 or equivalent to it. So 9 over 30, that can cancel to 3 over 10. So then r is equal to, if we bring the h up and multiply it, it'll be 3h over 10. So wherever that height is, that ratio will stay the same. So the radius will always be 3 times the height and divide it by 10. So now back to this volume formula. We can now say the volume is equal to 1/3 pi 3h over 10 squared times by h. So this will be 1/3 pi times 9h cubed over 100. And we can simplify that. The 9 and the 3 cancel, so we have 3 pi h cubed over 100. That means we can do dv by dh, differentiate this thing here. So the 3 pi over 100, that's just a constant. So we're focusing on differentiating the h. Bring the 3 down and multiply it, we get a 9 h squared. Oh, I missed the pi. 9 pi h squared over 100. Okay, back to working out dh by dt. We had this little bit up here. So we want dh by dt is equal to dv by dt times dh by dv. Well, we had dv by dt up here, minus 810 pi. We're going to times it by the dv by dh we have just worked out here. We need to flip that over to turn it into dh by dv. So times it by 100 over 9 pi h squared. Now those pi's are going to cancel and the numbers will do some working out as well. So 810 times by 100 and divide by 9. It's going to be reducing at a rate of 9,000 over h squared. So at 20 minutes, which was what was given in the question here, we need to work out the h. We do that by knowing that the volume is reducing at this rate here. So if it reduces by that much in an hour, it will reduce by 1/3 of that in 20 minutes. So you'll have 2/3 of the volume left. So the volume left will be 2/3 times 810 pi. So 810 times 2 over 3 is 540 pi centimeters cubed. Now the volume we've got on this line just here. Let's just highlight that actually. We're going to use this version here so we can get the height out of it. So if we set the volume as 540 pi is equal to 3 pi over 100 h cubed. Okay, so 540, the pi's obviously cancel. We're going to divide it by 3 over 100. And then we need the cubed root of that. Let me just sort this out. So our answer, cube root of it, is 26.2. So dH by dt will be minus 9,000 over 26.2. And I forgot the squared. So remembering up here, we've got minus 9,000 over h squared. So let's just try that again. 9,000 divided by 26.2 squared is equal to 13 point, well, that's a minus 13.1. The height is measured in centimeters and the time is per hour. So this means that the height is dropping at a rate of 13.1 centimeters per hour. Now for question 2, we have a product rule and a little bit of chain rule. So we've got the x in front here, and it's being times by log of, and then we've got a function inside of that, which is x square rooted, or x to the half. Just to be able to follow this easily, I'm going to separate them out. So we've got u equals x, v equals natural log of x to the half. So du by dx is 1, dv by dx is 1 over the thing inside of the natural log, and then times by the derivative of what was inside. Now that looks a mess. We can do some stuff to help out here. We can first of all put the 2 on the bottom of that from that half. The x to the minus a half is going to be the 1 over the square root of x. So on the bottom we have a square root of x. The x to the minus half that's on the top also becomes another root x on the bottom. So root x times x is just x. So then dy by dx is u times dv by dx. So that's x over 2x plus v times du by dx, which is log x to the half times 1. So that's just log square root of x. And the x's cancel, so we have 1 over 2 on that first term plus natural log of root x. Parametric equations for part B. So x is 4t to the minus 1. So dx by dt is minus 4t to the minus 2. Y is t squared minus 1, so dy by dt is 2t. So then dy by dx is dy by dt times dt by dx. So I'm going to turn that dx by dt into being a minus 4 over t squared. It's going to be easier to deal with. So dy by dt is 2t. Now dt by dx will be this one but flipped over because this one is dx by dt, so we need it the other way up. So we'll times it by t squared over 4. Actually, it's minus 4. Just correct that. So 2t over minus 4 becomes minus a half. We'll end up with minus t cubed over 2. We're doing it when t equals minus 1. So when t is minus 1, dy by dx is equal to, well, minus 1 cubed is minus 1. Then we minus it for this bit just here. So that'll be a positive 1 over 2. dy by dx is a half. Now My favourite types of questions, looking at the graph and figuring out the features that we're being asked for. Okay, so on this one, first of all, f of x is not defined. That means the x values where we couldn't get a value for what y should be, as in like there is nothing, there is no graph at that point. You might be tempted to look and see a gap here, but we actually have this one down here that counts when x equals 2. So the only gap we really have is where this asymptote is. So that is when x is 0.5. F of x is not differentiable anywhere that there's a gap, so we can write down the 0.5 straight away. We've already got that. Anywhere that there's sharp corners, or like two different graphs on either side, like this one here, that's not going to be differentiable. And anywhere where there's where the graph is discontinuous, there's a gap in the graph here, and it does something else at that point, so we can't differentiate it at 2 either. Now, the second derivative being greater than 0 means we have a minimum. So it's anywhere that the curve is concave up, and it's not just where the minimum point is exactly, but it's any part that makes that bowl shape. So we're looking for this bit here on our graph. Actually, let's highlight that rather than draw over it entirely. So it's this bit just there. That wasn't much better. Anyway, so it's the portion that goes between -2 and 0.5. Because all of that will make part of that bowl shape. Now the value of f being -1 just means that we put in, if we were to put in x is equal to -1, what value would we get on the graph? And we can see there it would be a y value of -1. And now the limit, the value of the limit as we approach x equals -2. So as we come towards -2 from both the left and the right hand side, are they going towards the same point? So from the left going towards -2, and from the right going towards -2, they both get to that same point there that has a value of 2, so the limit is 2. Okay, for this one we are finding the coordinates of stationary points, so that means we're going to differentiate and set it equal to 0. So let's start by differentiating. So if we are going to differentiate this function, we have a natural log to differentiate first and then this piece to differentiate afterwards. You just do them as two separate pieces. Now that 4 log of 2x plus 1 is going to be a chain rule, so this will be the natural log differentiates to be 1 over 2x plus 1. It got times by the 4 because of that 4 at the front, and it also gets times by the 2 that's on the inside, so the derivative of the inside there. So that becomes 8 over 2x plus 1. Now, minus x over 2 is the same as if we'd said minus a half x. So if we're going to differentiate that, it then is just minus a half. Now we're going to set that equal to 0 because we're looking for stationary points. So working through that, we can take the half over that side, bring the 2 up and multiply it, we've got 16. Bring the 2x plus 1 on the other side and multiply, we've got 2x plus 1. So 2x is equal to 15, or x is equal to 7.5. Now we have been asked for the coordinates, not just the x value. So now we need to substitute that in and work out the y. So this will be 2 times 7.5 plus 1 minus 7.5 divided by 2 gives us that y would be 7.34. And finally, we need to identify their nature. So that requires us working out the second derivative, f double dash of x. Now I'm just going to rewrite that as being 8 2x plus 1 to the minus 1, because then it's easier to see the chain rule. So minus 1 times by 8, we're going to get a minus 8, 2x plus 1 to the minus 2, and then times by the 2 that's inside for the chain rule. And then minus a half differentiates to 0. So when x is equal to 7.5, f double dash of x will be, so if we do 2 times 7.5 and add 1, it's going to be 16. So it'll be minus 8 times 2, there is a minus 16, over 16 squared. Now that is going to be a negative number. That's all we need to worry about at this point. And because it's negative, it makes it a maximum. Okay, for part E, we've got this function, and we need to find the second derivative and set it equal to 0. So first derivative, let's start with that one. E doesn't change, but we do need to times it by the derivative of what's inside of that function, which is the a over x. I'm going to write this as e to the ax to the minus 1. Let me just get that on screen. And if we differentiate ax to the minus 1, we get minus ax to the minus 2, which is the same as if we write minus a over x squared. Now we need to differentiate that again. Now we have product rule. We could also think about this as quotient rule, and the answer in the back of the book does give quotient rule, but since it's already written like this, I'm kind of inclined to go with product rule instead. So that's where I'm going. We've got our first term is minus ax to the minus 2, and the second term is e to the power of a over x. So if I differentiate u, we get 2ax to the minus 3, and differentiating v, well, we did that already. We got this one, so I can do that again, because this is just the same as what we had in our first function here. So that'll be minus a over x squared e to the a over x. Be careful, make sure your a's look like a's and not 9s. So then the second derivative will be, we've got to times those two together. So we've got a squared over x to the 4 e to the a over x, then times these two together. 2a, actually let's write this as 2a over x cubed like this, e to the a over x. And finally we need to set that equal to 0. So if this was equal to 0, we can first of all take out a factor of e to the a over x. We get a squared over x to the 4, 2a over x cubed is equal to 0. Well, e cannot be 0. If you were trying to work that out, you'd get a math error, because you would be trying to do natural log of 0 on one side, and that is not possible. It's an invalid solution. So therefore, we must carry on with a squared plus 2a over x4 and over x3. That's got to be equal to 0. Now, if we put that all over one term, that needs to be all over to the power of x to the 4. We would need to introduce an x on that 2a term to make that equivalent. Then if we were bringing the x4 up to the right to try and solve this, that would multiply away to 0. So 2ax must be 0. So 2ax equals minus a squared. So x must be minus a squared over 2a. Those a's cancel, so we have minus a over 2. And there's all of that on one page. Okay, question 3. For question 3a, let's start by rewriting this thing in line, so it's a bit easier to see what we are doing, like that. So that squared on the bottom becomes -2 when we bring it up. So dy by dx will be 8x, and then the -2 times the minus in the front becomes a +2. The bracket gets reduced by 1, so that's a -3. And then it gets times by the derivative of the inside, which is 4x cubed. If you want to tidy that up, we would have 8x plus, we've got an 8x cubed over an x to the 4 minus 1 cubed. Although it's not necessary to do that step, you can leave it as this first line here. For part B, we've got the distance equation just up here in blue. T is the time in seconds, and we want to work out the velocity. So velocity is the derivative of the distance equation. Now that distance equation, I'm just going to write it in brackets like this. So that's a chain rule. Half times by the 4 is a 2. T squared plus 1 to the minus a half, and then times by the derivative of the inside, which is 2t. And then minus t differentiates to -1. So that simplifies to being 4t over the square root of t squared plus 1 minus 1. So when the time is 4 seconds, the velocity at 4 seconds will be to do 4 times 4 divided by the square root of, we're going to have 4 squared, which is 16 plus 1. So the square root of 17, 17, and then -1. And we are measuring our distance in centimeters, and our time is in seconds, so it's centimeters per second. Parametric equations for part C. You probably need to look these ones up on the formula sheet. So dx by dt, differentiating cosec, we get minus cosec theta cot theta. It's on the table on your formula sheet, so don't worry about it too much, just look it up. Dy by dt, well, sine differentiates to cos, so we get 2 cos theta. So dy by dx is dy by dt times dt by dx. So dy by dt is 2 cos theta. dt by dx, that's going to be 1 over minus cosec theta cot theta. So let's tidy that up and see what we end up with. So we've got 2 cos theta. Now cosec is 1 over sine, so if that's on the bottom, it's going to bring the sine to the top. Let me just pop it over at the side here so you can see what I'm saying. So cosec is 1 over sine theta. So cosec is that. So if we were to do 1 over cosec, it's 1 over that thing, which flips the fraction over, which would then just become sine theta. Similarly with cot, that's 1 over tan. So this is sine theta, tan theta, and it's a negative. I'll pop the negative at the front just there. Now tan, if we sort that out, it's sine theta over cos theta. So that cos cancels with that cos, and we end up with -2 sine squared theta. Now that's not quite what we wanted to be able to show just here. Let me just tidy that up, it's not showing so well on my screen. Let's just pop in the missing pieces there. So that's equal to cos theta minus 1. So let's use our trig identities to turn that into something that uses cos theta. Now that is that cos 2 theta is equal to 1 minus 2 sine squared theta. So minus 2 sine squared theta is equal to cos 2 theta minus 1, just by rearranging that. So therefore we can say that this down here equals cos 2 theta minus 1, as was required. Don't worry about the QED notation. Sorry, I did that out of habit. It's a Latin notation for quod erit demonstratum. It literally means so I've shown it. It's a nice way of finishing off the question when you've shown something you were asked to show. Absolutely not necessary, just a little bit of nerdy maths that you can put in there. Part D, we've got rates of change. Now let's call this distance here x. Then we're told that the speed that this lead cyclist is traveling at is 18. So we have a rate. So the rate at which x is changing over time is 18 meters per second. That's how fast he's going. Now, as he moves along and the camera tracks around, then it's going to change the angle that we have just here. And the rate that we want to work out is how fast that camera angle is changing. So we want d theta by dt. Now to get that from dx by dt, we need to times by d theta to introduce the theta and divide by dx to cancel that away. Okay, so we now need something that links the theta and the x together, which we can do using trigonometry on this triangle here. We've got the adjacent at 50, the opposite at x, so we can use tan. So tan theta is the opposite over the adjacent. So x equals 50 tan theta. And so dx by d theta, well, if we differentiate tan, we get sec squared. So this is 50 sec squared theta. Now sec squared, we're going to put this into our calculator at some point, so it's easier if we write that as 1 over cos. So sec being 1 over cos makes sec squared a cos squared on the bottom, like this. Okay, back to our rate that we were trying to work out over on the left-hand side. So this now, dx by d theta is 18. D theta by dx is this thing here but flipped over, because that was dx by d theta. We want d theta by dx. Oh, I've lost a d. Okay, so that's 50 over cos squared. So this will be cos squared theta over 50. Now back to the question once more. We're working this out when the lead cyclist is 20 meters away from the finishing line, which means that x is equal to 20. So when x is equal to 20, we have 50 tan theta is equal to 20. So theta is equal to, let's do 20 divided by 50, and then inverse tan gives us 0.381 radians. And then we can put that into working out d theta by dt, substitute it into this line here. So we'll do cos of that answer, then square it, divide it by 50, and times by 18. That gives us the rate that this angle is changing at. Now the angle was measured in radians and the time is measured in seconds, so it's radians per second. Okay, final question from this paper now. We've got some information about this circle. We have the angle inside on a diameter. We know that that's always 90 degrees, so I'm just going to write that on before we start thinking about anything else. When we have a diameter and we have this set of lines coming out from the edge of that diameter to make a triangle, it always makes a right angle at the circumference. That's some laws of circles that you will be expected to know. Okay, so we have a right angled triangle here. We want to work out when the perimeter is a maximum and show that when that happens, those two sides will be the same. to make an isosceles triangle, and then find what that perimeter is, what that maximum is. So we need quite a bunch of stuff with this one. Let's start by working out the thing we need to maximize is the perimeter. So how do we write that down? That, of course, will be 8 plus x plus y. Now, we can't differentiate that yet because it's mixed up in x's and y's. We need to express either x in terms of y or y in terms of x so that we can then differentiate it, set it equal to 0 to find a maximum point. Right, so we're looking for something else that links x and y's together. Now we have, of course, got a right-angled triangle there. So we know that x squared plus y squared is equal to 8 squared. So x squared is 64 minus y squared, and x will be 64 minus y squared to the power of a half. Now we could, of course, just as easily have done all of that with making y the subject. If you do it that way around, that's totally fine as well. You'll have exactly the same thing, but the x's and y's will be switched over. Okay, now in the perimeter formula, I can replace the x with it being 64 minus y squared to the half, which means we have everything all in terms of y, and I can differentiate dp by dy. So if I differentiate in terms of y, the 8 is gone. We have a half 64 minus y squared to the minus a half times by the derivative of the inside, which is negative 2y, and then plus y. Sorry, not plus y, plus 1. If we differentiate y, we get 1. We're going to set that equal to 0 because we're looking for a maximum. And now let's do a bit of tidying up. So the 2's cancel here and here. We will have a minus 1 over the square root of 64 minus y squared plus 1 equals 0. So I can bring this over to the right-hand side, and we will end up with that is equal to 1. And I've just spotted one little thing. I forgot this y in here. So we do actually have a y on the top just there. Okay, so if I bring this up to the right-hand side, we now have y equals the square root of 64 minus y squared. So if I square both sides, we've got y squared equals 64 minus y squared. So 2y squared is 64. Y squared is 32. So y is the square root of 32. And now we've got y, we can put it into this equation here. So x is the square root of 64 minus y squared, so that's 32. Well, 64 minus 32 is also 32, so that's the square root of 32. So x equals y when p is a maximum. So we've shown this bit here, show that it will be isosceles, and just for completeness, we'll say therefore isosceles. And then the final thing is to find the maximum perimeter. So we're putting it into this equation just here. So 8 plus root 32 plus root 32. So 8 plus 2 root 32, or 8 plus 2 root 32 makes 19.3 centimeters. There we go. We're all done. That brings us to the end of the worked solutions for the differentiation papers for the D&D resource booklet. If you found this helpful at all, please like and subscribe, share it, do whatever. But any interaction you can have with the video helps other people to find it too. And then there's my homepage to my channel that will have a whole bunch more stuff that I'm sure you will find useful as you get ready for these exams. So hopefully I'll see you engaging over there too. Thanks. Bye-bye.